Welcome back to Green. Francesco and Emma here. Em, how's everything?
Good, thank you, Francesco. You sent me away to do some research on this week's topic. Plastic, polystyrene, foam. And I only came up with one big number, but it's a big number. The amount of EPS foam production in Europe alone is 2.27 million tonnes. The plastics industry is facing massive price hikes in raw materials, oil, and energy costs because of the war in Iran. But there is a good news double whammy coming in because new regulation finally is explicitly making sure that plastic is designed for recyclability, and packaging that's non-recyclable will get an immediate price hike of 20%, escalating up to 100% price hike by 2028. And the final thing is that the EU, I do identify as European despite Brexit, has completely banned the export of plastic waste to non-OECD countries, and that will be trapping 800,000 tonnes of plastic into the EU every single year.
As you may have guessed, we're talking about plastic today, more precisely about foam. It sounds basic, it is not. And by the way, not the foam in your cappuccino, the foam that protects your deliveries, insulates buildings, keeps food cold, fills packaging, cushion products, yada, yada, yada. The problem is simple. A lot of this material is still fossil-based, cheap, brilliant at its job, and terrible at disappearing. We use it because it works. We hate it because it stays. And that is exactly where today's guest comes in. Elizabeth Lee is the founder and CEO of Carbon Cell, a company trying to do something that sounds simple, but is incredibly hard. Build a plastic-free foam using biochar and natural materials that can compete with conventional fossil-based foams. Liz, welcome to Raw Green.
Thanks for having me. So excited to be here talking about, all of that problems, all the opportunities, foams, my favorite.
That's it, Liz. Polystyrene, as we regularly know it's everywhere. But it usually only has a short attention span for most people. You know, you open a box, you discard the packaging straight away, you don't think about it. So let's start there. What is this plastic foam, this polystyrene, actually made of? Why is it so useful, and why is it such a nightmare to dispose of properly?
So the history of polystyrene and expanded polystyrene is really interesting because I think it was one of those accidental creations by DuPont in like the 1950s. And it is a really useful material. It's very lightweight because it's 99% air. And it makes it a really good insulator. It's also made out of one of the cheaper types of plastics. Polystyrene's also injection molded, but in this case it is foamed through the use of gas injection. And it's widely used because it is very cheap and it is very good at insulation. But those are actually the things that, some of those things are actually what makes it very difficult to actually dispose of properly. So if you think about recycling, there's economic value derived from taking back goods. So it's not just about we do this for the benefit of the planet. Usually recyclers have their own business models. They need to ensure that the materials they reclaim actually have enough inherent value in them to be reconverted, taking into account the logistics of doing that. So actually going around and collecting all the little bits. And things like expanded polystyrene, and it's not the only product that has this issue, but because they are 99% air, there's not a lot of material to be reclaimed for the volume that you can collect. So you picture a truck or a lorry, depending on where you're from, going around collecting recyclables and crushing them up. There's not a lot of polystyrene that you can fit on that. And therefore there's not a lot of value that you can reclaim. And on top of that, it seems very maybe obvious or silly or stupid, but they are lightweight, so they blow away.
Yeah.
There's a leakage problem is the technical term in the industry, which applies to a lot of recyclable or non-recyclable materials where they leak outside of waste collection systems because they blow away or can't be collected or contained, and they end up therefore in waterways, on the street, in the sea, all sorts of places.
If anyone splits a beanbag, they know exactly the pain we're talking about.
Exactly. Yeah, nurdles. And that sort of that makes them one of the key key worst plastics in terms of actually ending up degrading into microplastics. It's not because they aren't recyclable, and I think recyclable is a word that actually we should always question a little bit. They are very recyclable, but they are just not very commonly recycled for these other factors that have nothing to do with the material and how good it is at doing its job, but more to do with where it comes from and what it ends up as.
So, Liz, run us through the different types of products that we have out here. And when we think of these plastic foams that you're working with, are there lots of different types of foam? Do they serve all different purposes in the sort of sectors that they're across? Give us a broad intro to that.
Yeah, so foams is a really interesting segment of materials because they're commonly very invisible in the world around us. They may be inside a lot of products, hidden behind an exterior veneer or surface. So they are used in buildings as insulation materials for thermal resistance, for acoustic resistance. So they might be in your walls or in your ceiling or in your floor. They are used in textiles and footwear and furniture to add volume without adding weight, and often to add sort of resilience. They're used in packaging. They're used inside actual products in things like automotive design, where they're trying to make everything super lightweight. They need to be adding structure without adding
Wait.
additional things
Mm.
like a steel chassis. So they're moving to more composite design where there's carbon fiber exterior and there's foam inside. So there's a wide range of different application sets for these materials, and they come in, I mean, it's an alphabet soup of different acronyms. Expanded polystyrene is one class of material. There's expanded polypropylenes. There are TPUs and eTPUs, expandable TPU. There's all sorts of different polyurethane foams, and these classes of materials can be made in different ways. There's broadly two classes. There's particle foams, which might be beads or nurdles of material that are expanded using heat into molded forms, or they might be extruded. And then there are chemical blowing agent foams, which have sort of two-part reactions where if you want some entertainment on YouTube, you can Google them. They add these two materials together and it explodes like a volcano. So yeah, there's a wide set of materials with different properties that sit within that broad nomenclature of foam.
So, what are the current options here for once you've made it? What are the recycling rates? What is the end of life for these? I mean, I can imagine they would burn fairly readily, and I imagine some of it's buried in landfill. Do you have any stats on sort of what ends up in the sea versus what potentially could be or is recycled at all?
Yeah, and this is where data is very difficult to find reliably. You might look at one source, British Plastics Federation, and find that 30% of these materials are collected and recycled, and 30% is good. And you have to sort of question like who is collecting the data from where? Is that actually good? What is
Very good
good
point.
look like? It's very hard to collect reliable data about those kind of things, which makes the problem feel hard to tackle. And recycling rates vary widely across different regions. And you never really know, even if it's collected by a recycler, where that product then ends up. Is it getting downgraded into something else, or is it truly being recycled? So I think one of the biggest problems is lack of data about that. Truly, as I was looking in advance of this podcast, I realized like how much of a problem that is that we just simply don't know.
And well, look, the data issue, it is across the spectrum, to be honest. And for me as well, while I was preparing some stats for this episode, I came across. I was curious to know what is the percentage of oil extracted that goes into the production of petrochemicals, and then more specifically, then what goes into plastic. I found out that over 85% of the, let's say, oil extracted goes into energy. So whether it is for electricity or any other or thermal, and then 12 to 15% goes for petrochemicals. 4% total of the oil extracted goes for the production of plastic. The point of all these numbers, it is because we are living into a particular time right now where, while before the proposition of sustainable products was because of the good of the environment and the betterment of the environment, right now it has become clear even to the most blinded or deaf person that it is important to be independent, not just now from an energy perspective, but also from a material perspective. So it has become of sovereign importance to have internal production. And I was curious to hear from you if there is, as it has happened for the energy, right, where solar and wind took over like lions, and the deployment, you can hear almost every quarter that they're beating some sort of record across nations, across continents, not just in power installed, but also in actual energy production. The latest was this morning from the US. I was reading in the solar was the primary source of energy production last week, and it was incredible, right? The US, that is right now not particularly friendly towards renewables. I was curious to know from you if in your industry there is a solar and wind equivalent.
Yeah, I mean, I think there is a growing trend if you look at a regional independence as a key political driver of investment and also innovation now, um, in growth of new materials as not just sustainable options, but actually as ways of disconnecting from that oil supply chain. So I think one example that has been studied because it's a little bit ahead of the curve in maybe other sectors and industries is the built environment and the use of
Yeah.
bio-based insulation materials, or at least non-plastic insulation materials in the European Union due to policy changes that have sort of prioritized localized sourcing of materials. And also due to sort of political climates where those types of materials have a sort of pride associated with them about being made in the region or contributing to the local
Yeah.
economy, actually interest in buying them, and sort of disconnecting from having to buy from overseas. So I think that's one where we really see it. I don't think there's one single material, same way there's no one single energy source that can really replace um, the oil equivalent, or be the sort of one single competitor that fits. And that's actually the point, is that we should be sort of distributing the use of these materials across where they are appropriate, where they can be locally sourced, rather than trying to seek one single alternative that really works on the same long supply chains, globalized, consistent way that oil does, because then we'll just end up creating another one of the same
Same
problems
issue. Yeah.
with natural
Yeah.
resources. But yeah, we are seeing it. Different industries and sectors have different stages of development and drive to do that. And I think yeah, construction is one of the bigger ones because it's been under a lot of fire for um, causing a lot of emissions, and often you are dealing with you need to get planning permission for things. There's more oversight into what materials are used and when. Other sectors like fashion have obviously considered this, but have not yet really successfully transitioned their supply chains away from um, the sort of like long globalized systems that exist, because I think it's much harder and there's less regulation, there's much more cost driving, there's much faster cycles of development. The longer cycle of development you have, the more chance you have to really think about considering where you're sourcing from. The faster it goes and the cheaper it is, the less time you have to think about that. So yeah.
There is an incredible pressure also. I mean, the built industry, it is obviously one of the largest industry in the world, with an incredible power of purchase, right? But I have seen across Europe, not only actually, also in Asia, a push, not just at regulatory level, but from builders to work around and understand the emission, the whole life cycle emission of their products. You have the RICS that they came out with their whole LCA model to be able to quantify from the very beginning. So there is a push on there, which is fantastic. The EPD system, the environmental product declaration system, basically it is for the built environment. So it is that I agree with you 100% on the fashion industry. I do have lots of friends that works into the fashion industry, both in Asia and in Europe, and they tell me, say, we're still behind, like a lot behind. Their communicate, even their communication strategies, they got burnt a lot. They got burnt a lot with the various H&M and others that they were throwing these incredible statements of green credentials, green products for them being hammered very violently of greenwashing. So I think they got burnt a little bit, but they're not the only one at all.
Yeah, they can move fast. The construction industry moves slower. I do like to see the progress there, but we're not seeing it really come through in the procurement cycles and things. It is notoriously painful. But Liz, tell us why for you, why foam? What's your journey? And tell us a little bit more now. Let's get into carbon cell and what you've actually managed to try and address.
Yeah, why foam? I mean, I think it's something that I find fascinating, like almost problems. They're not orphan problems, but you like to adopt a problem that hasn't gotten a lot of love yet. So I find those actually really technically interesting, and foam is one of those sectors that, compared to thin film plastics, compared to rigid ejectables, like hasn't really gotten as much love. It is technically challenging as well, and you're up against some of these very, very low cost materials, so that makes it an extra big of a challenge. So I think part of me is just interested in solving something that hasn't really been solved yet, rather than improving on the work that has been done. Trying to do something better um, than something that's already been developed. In sustainability, I guess one of the challenges is always you get pitted against other sustainable products rather than talking about the larger problem of unseating oil. And I think in foams, it's an area that's fresh and new enough that we can talk about the real problem, and we're not just stuck in this cycle of trying to deposition ourselves against other sustainable alternatives.
So what was
Whereas
the
talking about
aha
other plastics
moment?
do that. Yeah. The aha moment, I mean, so just the backstory on the company that we developed this technology while myself and my co-founders were at Imperial College and Royal College of Art, and we were looking at biochar as an interesting technical material. And biochar, for anyone who doesn't know, is a type of carbonized agricultural waste that derives from any sort of agricultural waste. You might even non-agricultural waste like sewage sludge can be carbonized, and it's become more popular over the years because not only is it a really interesting way of converting waste into useful products, but it traps any carbon that plants have sequestered over their lifespan into a format that's very stable. So it's a tool for carbon sequestration, and some estimates say that biochar, if it were fully scaled, could absorb up to 35% of the world's carbon reduction needs. So it's a relatively scalable, mature technology, and it produces really interesting technical materials that are types of carbon that are very porous and lightweight. And anecdotally, that has been shown to improve soil resistance to thermal stress, and it's been used as technical additives in things like concrete to reduce weight and add thermal resistance. So we thought those are really
Water
interesting applications
purification.
for the
It's
material.
got
Water purification,
so
yes,
many
exactly.
usage. Yes,
Yeah.
it's
And
incredible.
as biochar is becoming more popular, people are producing more of it, there is a need then for the economics of that to work out. So
Of
more
course.
technical uses for this carbon resource where the carbon can be permanently stored, where more uses where those technical attributes of lightweight, thermal resistance, water absorption are actually adding to performance of materials. And so we thought foams are a really interesting category where those are exactly the things that you need. You want something that is lightweight and porous to add thermal resistance and strength. And in the biomaterials segment, this capability of moisture buffering or being breathable is actually really interesting as well. So what if you could create a biochar foam? and elevate both of those attributes. And that's really where our research started at the university. We looked at conventional foaming systems, different types of co-materials you could add to evaluate what types of foaming work within this type of composite. And the aha moment was really landing on where we landed, which is this type of natural polymer, thermoplastic starch-based polymer, where you can mix it with the biochar and treat it similarly to how expanded polystyrene is manufactured, in that when you expose it to heat, there is a gas trapped inside and it expands rapidly, and you get a sort of a foam structure forming that you can then mold and shape. So the aha moment is literally seeing the inflation of this material for the first time, and we sort of followed the science and successfully got it to form a foam structure, and then tested it and found it had all these really interesting properties.
Let me ask you something, Liz. When I read about carbon negative products, normally I start to itch behind my ears. I have like a allergic reaction because usually it is something that in many cases, not all the cases, it has been just thrown there into the communication strategy of a product or a process. I'm curious to know about your carbon negativity.
Yeah, and it's a really good question that I think like more people should be asking, because I mean there was a mention of greenwashing earlier. Like, all of these solutions are only as successful as how well people understand them, and if there's any backlash, we actually shoot ourselves in the foot in the long run. So I think it's really important to be completely transparent about what can or can't be carbon negative. When we talk about carbon negative, we talk about the balance of a comparative scenario. So you have always a material that you're replacing, and how much more or less carbon than that material does your process produce. So that's sort of the overall framework, and setting the bounds of the life cycle. You're always doing a comparative scenario. So in many
Right.
cases, you really want to be looking at what is that comparative scenario to be ensuring that you feel like you can believe the data that someone who's claiming carbon negativity um, can share, and see if you actually believe in that framework. For us, we're looking at comparing against different materials, and the balance of how much better our material is depends on that material. So in comparison to expanded polystyrene, we can improve or reduce carbon by a certain amount, but in comparison to cardboard, it might be a different amount. So when we say carbon negative, it's very important to have like an asterisk with that, and we are really careful about that, saying in these
Very good.
contexts. Biochar itself is considered carbon negative because,
It's
as
a
I
saint.
mentioned, like
Yeah.
plants are sequestering carbon through
Yeah.
photosynthesis at their lifespan, and normally when they die or are harvested, that carbon dioxide gets re-emitted either as methane as they degrade naturally, or as carbon dioxide if they are burned to get rid of the waste. And so biogenic carbon is not permanent in that regard, it's re-emitted. So biochar is classed as negative because you're carbonizing that material into something that can remain stable for up to hundreds or more years. Um, and then when we use it in our product, we're looking at, okay, how much carbon was in that biochar, and then how much carbon was in the other materials and processes that we're doing. So how much is in our natural polymer, how much heat are we using, how much electricity are we using, transportation, other types of emissions factors for things like water usage are important to consider. And we sort of tally those up, and then we say at the end, like, we've emitted some more carbon in our manufacturing, but we've sequestered carbon in the material. So what is that balance of the material itself? And then, which depends, of course, on looking at like your scale of production as well as your source of raw materials. So there's all these different really important like details to look at when you talk about negativity. And then where does that product end up? So is it going to be permanent where it ends up at the end of its life? Is another important consideration. So in our case, if the foam that we make ends up like your expanded polystyrene on a beach, or in the ground somewhere escaping waste streams, it is still negative because the carbon contained in that material is still fixed. The biochar will not degrade. Our natural polymer will re-emit a little bit of methane, but we've taken that into account in our life cycle, so we know that net it can have a negative figure.
Very
Where
good.
we do need to be careful is what happens if that material gets burned. That carbon will then get re-emitted. So we can only really truly claim that it's negative when it ends up in certain areas, and we're careful about positioning that. And we haven't really looked at, from our perspective, the carbon market, the voluntary credit market is very complicated right now. So we don't sell any carbon credits based on our material either. We're not necessarily
That's very good to
claiming that
hear,
it is
Liz.
yeah.
And I do like it a lot that that your asterisks has let's say the salt in the brain that says it depends on from product to product. You know that English is my second language, so don't start to.
We'll go with
Yeah.
salt in the brain if that's how it
Well,
feels.
I like
know what
it.
I mean. You know the meaning.
Yeah.
Okay. What I
Yeah.
wanted to say, it is good that you have that asterisk because you have two different kind of biochar, can have two different completely
Correct.
carbon sequestration around.
Yeah.
My itchiness around biochar starts from the fact that at the moment there isn't a scientific metered methodology that is able to quantify with extreme degree of precision how much a plant it is able to draw CO2 from the atmosphere and drop it into the roots and into the soil. There are various formulas that changes widely between type of plants, between latitudes and longitudes. So the reason is not like direct air capture, sorry, where you have a meter that you're able to see exactly what is the volume CO2 drawdown.
Yeah,
So I
but
like that degree of variability. It is not an exact science yet.
I'm
But it's
just gonna
important that
gonna
you communicate
pull
that.
Francesco out of this little nosedive he's gone into like a tick with the carbon, because
With salt. Yeah.
climate is not the only impact here. As I mentioned before, we're in a plastics crisis. We are literally drowning in the stuff. It is a case
Yeah.
now of managing the resources that we have, both in terms of incoming with all of those supply chain issues and outgoing with the waste that we can't deal with what we've got. So tell us a little bit more about the product and its benefits and attributes, Liz, so that we can understand what it's like end of life, and again, what are these other benefits that can be brought to market with packaging and with some of these other products that you've referred to as well.
Yeah. So I think it's important in an attempt not to be selling at a green premium always, or selling just based on pure carbon
Wow.
sequestration, to look at the functional properties of the material and really just make sure that it's fit for purpose. So the material that we create has thermal resistance. So we use it in insulation materials. It has absorption of sound. So on different frequency spectrums, you look at how sound can pass through materials. So foams are really good often at diffusing and absorbing sound waves. So our material also has sound absorption characteristics. It sort of has a breathability, so moisture buffering capacity, which means that it can take up humidity and then release it again into the air, which can be helpful in terms of mitigating perceived temperature in rooms. It can also be helpful for air quality and not producing like condensation where mold can form. It has a high compressive strength, so it's very strong, which can be a benefit in both construction and packaging. And it is able to be sort of degraded, so that the biochar component I mentioned is very stable, but the natural polymer we use hasn't been modified. So essentially, in the manufacturing process, any pre-commercial waste can be degraded, and also at the end of life, it could be home composted. So all of those attributes sort of paint a larger picture of like, where does this help solve issues in the supply chain? So both from a functional perspective, like people are seeking alternatives to packaging that doesn't leak microplastics. So that's not a carbon issue, that's not a
Wonderful.
waste issue, that's a health issue, and materials like ours can help solve that. In the built environment, people are looking similarly for natural materials that are breathable, that don't have they don't off gas, or they don't produce condensation. They don't necessarily burn at the rate that petrochemical foams burn.
Yeah.
So we can help solve some of those problems as well. And the full picture of really like why is it better, why does it solve a problem is not just about the carbon at all.
So go
Yeah.
on, you did just touch on it. How does that perform then in terms of cost in relation to your fossil fuel incumbent?
Yeah, so and it's really important, I think, for us to show that in order to have massive impact, you need to be able to access a massive market. And so meeting buyer requirements for cost is really important. For us, cost parity comes at a relatively small sort of turning point, and it's mostly driven not by raw material costs, so not necessarily by the price of biochar or other raw materials, but just on throughput of production. I think when we look at that compared to other sustainable materials, that's been the issue. Is the supply chain is really not robust enough. So there may be not enough seaweed materials, not enough refining of, you know, fermented things. Biorefining is not scaled up yet, so they have supply chain constraints. We don't necessarily have the supply chain constraints. We need to reach a certain manufacturing scale, and then we can compete on cost directly with conventional plastics.
Directly. Tell us a bit more about that supply chain, because of any startup that's basing itself on using waste as a resource has inconsistency of supply, doesn't it, in terms of different properties and different qualities, as well as different quantities. And of course, particularly with something like biochar, there might be a seasonal nature to its price and its availability and things as well. Tell us how you're coming across that.
Yeah, so it's one of our areas of like IP that we've developed actually is sort of navigating the variability of this raw material and understanding what characteristics can be controlled for or processed to mitigate variability and versus which ones you can't control, and therefore you need to be selective about suppliers. So we've collected data over 60 different types of biochar now from every continent except for
Wow.
Antarctica, just to validate and understand the flexibility of the system. So like how much variability can we accept and still produce like a foam that meets certain
Consistent. Yeah.
specifications. And then within that, there is still variability. So then how do you control for it? How do you measure, categorize, and then retroactively sort of update your process in real time to control for that input variability? So that's one of our core areas of expertise and IP that we've generated, is really just knowing how to deal with the variable resource. We also have to develop relationships with local suppliers who have scaled up. And I think that's a good thing with biochar, is that there already is sufficiently large supply for us of
Is it?
producers who are already, there's loads of biochar out there. I mean, some of our suppliers are throughputting 30,000 tons a year from one facility. Um, there there's a wide enough variety of supply out there at sufficient scale already for us to work with, and working with those producers directly, it benefits them and us. They want a buyer, they want off takes that are consistent. We can say, you know, if you work with us on uh, making sure that your process is consistent enough and you measure for these things in your production, then we'll commit to buying it. So it's relationship building in each geography as well. So we don't have to be shipping stuff from Asia to the UK or from North America to Europe. And then it's developing the sort of technical knowledge to characterize and then update the process according to each different variable feedstock.
Sorry, Lisa, but what Emma was saying earlier, and I have to say I like you because you didn't answer the question at all about the cost. You took it
Oh, she
so
did.
wide. Look at that smile. She's smiling with 87 teeth. She got it so wide. The reason why I'm asking you this, it is countries wants to decarbonize their supply chain, okay? But you have to give them an alternative. And
Yeah.
I'm sorry to say, climate tax, obviously, they have double the burden, double the complexity in delivering some products, because they have to deliver both on environmental claims. But if you want to really get the product onto the market, you also need to have that cost. You know, to have that attractive cost proposition. So I was doing again a little bit of research and find out that biomaterials in general, okay, they tend to be between 2 to 4 times more expensive compared to their synthetic or fossil-based counterparts. Now, you said when we reach a certain degree of scale and production output, we will be able to be in cost parity compared to
Hmm.
the fossil products. Where are you now?
Yeah,
How far are you to be say, okay, we're going to smash these guys. We are going to take over the market or
yeah.
not? How far are you?
So right now, the products that we sell, it really depends on the category, and I think this is where I'm not trying to be purposefully evasive, but when you talk about kilograms of material, there's a different
Yeah,
pricing versus unit economics of a molded object that has like other manufacturing
yes,
considerations
of
like
course.
tooling, minimum order quantities, all sorts of other constraints.
Yeah.
So if we can look at it on a raw materials basis point, and I think it's like 4 times more expensive right now, of course, or even more depending on like how much we're running the machine downstairs and how many people are overlooking that machine. But when you look at 2028 figures and the scale of production we estimate to be producing on there, that's where the kilograms basis becomes much more affordable. So it's
Sorry,
not
Liz, but this
too
is
far along.
extraordinary. This is fantastic because if you no, I'm telling you why. It is not negative. It is actually extraordinary. I'll tell you why. If you're now 4 times more expensive and you are early stage, okay, it's a very young venture. Where are you now? So if you're now 4 times more expensive, it means that really what you said earlier has a mathematical, an arithmetic base to say, okay, in 3 years' time, in 4 years' time, we will be able to have the same cost per kilogram or per cubic meter in your case, maybe, because we're talking about volume more than weight. Compared to the ginormous corporations that produce this on the scales of the million tons per year. So it is a really good thing. It's a really promising thing. That's why I wanted to hammer a little bit more around this.
And how about the manufacturing processes? Do things need to change dramatically to work with your materials? Is there
Yeah,
a
so
cost benefit?
that's really one of the things that myself and my co-founders come from design and engineering backgrounds. So we're thinking about this not just from like chemical engineering perspective, like the actual formulation, but we're thinking about how does it fit into the system that may exist already. So that's um, one of the key proposition points that we wanted to focus on is how do we take pellets or beads of our material and then retrofit other equipment that already exists to work with that
Very good.
material rather than creating a new process that requires totally new factories. So yeah, the aim is to be able to sell through to existing thermoforming technologies, and there's a variety of different types of those. I can go into more depth, but basically in premise, you're applying heat to a mold in different various forms. And our material has a different specific heat capacity, has slightly different water content. So you'll vary different things like pressure, temperature, and residence time. You try to control for humidity, and those are process control things that do need to be worked out in order to retrofit the material to those machines. But we're hopeful that in premise, because what's happening inside the material is very similar. So a gas is expanding, similar to what is in expanded polystyrene. That if you adapt those residence times, temperatures, and humidity levels to process control enough, you can adapt to those machines to use our material. And we
Wow.
Excellent.
validated that. Yeah, we validated that at different stages at different technologies. So one of the most straightforward ones is just taking pellets and then extruding them again into sheets of material or even into like if you're familiar with like packing peanuts kind of format. That's one of the more simple processes, and that works. We validated that works with our material already. Some of the more complex ones where you're having like geometry control of draft angles and wall thicknesses that need to be very precise, like that's a little bit further out for us. It takes a bit more
Sorry,
time.
Liz, but this means that you already have worked out your scaling up, your production scale up, that you can retrofit already in existence machinery and processes. So you don't need to develop also a brand new process around your product. I'm curious to know, because it is a really hot topic right now, how it is, considering all of these premises, how it is going, the fundraising for you. How is that been and how is it going? Not because the scaling up in Europe, it is a huge, again, another sovereign thing that it is becoming more and more a topic of discussion around networks and sofas mostly. So what I was curious to know, since you already have all of this, I was curious to know how is it going for you.
Yeah, I mean, we did a pre-seed funding round last year, which closed in April. I think there was like a lot of, I mean, it was the first time I did like a large fundraise, and I'm first time entrepreneur. So I was learning a lot as we go. All my co-founders were learning a lot as we go as well. There's a lot of messaging you absorb as a founder around like how bad it is to be raising as a climate tech entrepreneur in the moment. Like everyone wants AI and defense tech. It was, difficult. And I think you need to explain a lot more, particularly like we're not solving a consumer problem or maybe like a broad market problem. So we need to educate certain types of investors about the problem in order that they understand the value proposition better. So that part of it, was like challenging. Some people just don't get it or they don't care, and that's fine. Everyone can connect from getting a TV, I think, and having like those plastic pellets over their like living room when they've unpacked it. So that became like a talking point that we we focused on. But it enabled us to get enough to do this first sort of demo plant that we have in London, where we're based, to do like extrusion testing and get enough pellets of material that we can then ship off to different manufacturers and start to do larger manufacturing trials and orders and that sort of thing. And now the stage is we will be doing a seed round fundraise more focused on getting, proving out that manufacturing trajectory that I mentioned that is necessary to get to cost parity. So do we take what we do on our small machine in London? What do we do if we do that on a machine that's 10 times larger? Like, does it work? And what sort of can we validate that sort of price reduction? And that'll be the focus when I start the fundraise this coming year or over the summer. So there's always a need to be no more funding. I think what's interesting in talking to people lately is that like the drivers of the conversation for us, it's some of the stuff we've been talking about, not necessarily carbon. It's about supply chain resilience. It's about human health.
Very good.
In some cases, like the dynamic between AI and hardware is really interesting right now because, yeah, a lot of money is going to AI because investors want to get a quick return and the bubble is like really good right now. But how defensible are a lot of those companies? Like if you're not the one creating the core IP of the learning models or the actual like tech inside the tech, like someone else can leapfrog you so quickly in this environment right now that how do you ensure that, how do you de-risk that? Actually a hardware product has a lot more value, inherent value, if you can get it right in many cases, because
Yeah.
it's much harder to steal and leapfrog work that just takes time, physical resources, and once you've built that out, like harder to replicate. So I mean, we'll see how it goes, but I think those are some of the dynamics that like I've been talking about with other co-founders and investors recently that make it feel like maybe less of a difficult. I mean, it's still probably going to be a hard time to fundraise. It's always always
It's
feels
the
like you should have been alive a little bit earlier in time, and it would have been better. But
oh yeah, hindsight when's a fundraise, and 2022
yeah,
was definitely it. No, there
exactly.
are tailwinds though, like I mentioned with the regulation right at the beginning. There was a shifting landscape that you're in now. Do you see big potential markets in Europe, worldwide? Where are you going to head to first? What's your beachhead?
Yeah, so I mean, the UK is home for us, so that'll be the first test ground. And there's a lot of support for
Yes.
localized manufacturing right now politically, which is great. It can be a point of alignment across political lines, and supply chain resiliency, advanced manufacturing are really key points for the UK right now. Um, Europe,
Yes, it is.
mainland Europe is a massive market for us as well. I think the comparison point in terms of the manufacturing base is like 300x the number of polystyrene producers. So
Yeah.
just like a massive, much more developed market for us to sell through partners there.
Yeah.
And then North America will be our next market beyond that, because I think there's huge opportunity from it's just a massive opportunity for the built environment as well. Slightly different, slightly less regulated. Yeah, huge, and of course a lot of investment coming from that region as well. So good to be operating there as well as getting funding.
Absolutely,
But
Liz. So what's your vision for the future then for Carbon Cell? What does the future look like when Carbon Cell is big and, taken over the world, and what do you need beside the funding, obviously?
Yeah, I mean, I think we see ourselves as another one of those acronyms in the long run, sort of that you could go and specify our material on any sort of molded product you might want in terms of foam. Um, I want it to be unique and have huge impact, and that requires being sort of an omnipresent name, like just as much as a big chemical company might be producing branded styrofoam, carbon cell could be on that scale. And that's really where I want it to go.
wonderful. Thank you, Liz. This was a really nice conversation. Like we all said, there is a need to detach from the oil supply chains, not just for environmental reasons, but for an array of other reasons, which we have listed numerous times today. Thank you for being on Raw Green, and I look forward to catching up with you very, very soon.
Thank you,
Yeah,
Liz.
awesome. Thanks for having me.
Thanks for listening to this episode of Raw Green. If you made it this far, you probably enjoyed it. So don't forget to hit subscribe and follow our podcast. It's an awesome way to support our community. At Obi, we're all about research, life cycle assessment, and the green tech innovation. Stay in touch through our socials or visit our website. Links are ready for you in the description. Catch you in the next episode. Ciao!